Hello, it's February 22nd, 2023, 22223, and we're in the second discussion of Chapter 7 in Cohort 2. Before we go to the questions of Chapter 7, and then at the end a look ahead to Chapter 8, we are going to have Thomas Parr join for a live stream in 5 days. And so anybody, if they would like to raise an area of questions, could be conceptual, or it could just be a general textbook level or personal question. So of course, feel free to add anything, but just while we're here, any thought or like kind of general piece that people are thinking that Thomas could reduce our uncertainty about. All right, just, of course, add it when you see fit. Okay, there were several questions that we've already looked at from 7, and several more. We can also look a little bit more, just again, we looked at the first sections of the chapter itself. So, does anyone have a Chapter 7 question that they want to go to or add? Or do they prefer to walk through the sections in the textbook? Let's look at equation 7.4. See if we have anything annotated for it. Okay, we don't have the natural language yet. So let's just look let's pick back up with the rat in the maze example, go through it, connect it to the equations, and then return to several of the questions down here in 7. So in the earliest part of Chapter 7 was a passive inference with the example of listening to music. Now, the upstairs action selection part is going to come into play. The imperative for action selection is going to be G. G, like we saw in Chapter 5, takes the action prior, the prior on different policies, which can be understood as like habit, and then sharpens it according to, just qualitatively, provide epistemic and pragmatic value, and quantitatively, as described in equation 2.6 and 7.4. Does anyone want to give a reading or a thought on 7.4? Just what is it saying in and of itself? And or how does or might this relate to, in their words, the resolution of the exploration-exploitation dilemma? Yeah, Ollie, go for it.
Well, yeah, as we saw before in Chapter 2, I guess, but I think it was in a more comprehensive terms. But here we only have a part of that equation, which basically deals with the trade-off between epistemic value and the pragmatic value. and how they relate to each other, because as we saw in chapter 2, the trade-off or the dilemma between exploration and exploitation is basically one of the fundamental requirements for any um sentient behavior, for any sentient agent, because as long as the agent tries to uh, wants to explore the environment in order to um, informally discover new let's say opportunities or new resources, be it I don't know, food resource or any other resource necessary for its survival in the environment. It needs to somehow have a trade-off between this kind of having the pragmatic value on one hand, namely to survive in the environment, and on the other hand, to discover new resources for its survival, which basically relates to the pragmatic value. But either of those two requirements, if taken to its extreme far, would probably result in the demise of the agent. Because so take, for instance, an agent residing in an environment, but for a certain period of time, it can't survive in that environment using the pre-known resources there. But when the resources is about to to diminish, then that agent need to explore a little bit further in order to discover some new resources and continue its persistent through time or its survival.
Yeah, great. Yes, Michael.
Yeah. So I'm a little bit wondering, the in these epistemic considerations, only things can be considered that the agent actually already knows about, right? And then I'm wondering why at several places, I think it said this in chapter 2, and here in this chapter 2, also 7.2, also that that one would like to find the most unlikely path, or one would like to increase the information value. Means one, that's what I understood. So the path that should be searched for would be the path that maximizes information, which is means it's the most uncertain path. And
I mean,
incorrect?
There's aspects that I think are correct, but I just want to draw that out. So actually, what is being selected for policy are the most likely paths. What is an agent like me most likely to do? We're sampling our actions from the action posterior. So rather than scaling policies by their reward and ranking them by their reward in reward learning and choosing sampling from the reward posterior, for example, we're going to be sampling from an action posterior. So in the sense that our actions are selected based upon their posterior likelihood, we're actually pursuing the most likely path of action, indeed the path of least action. However, we are seeking, in the epistemic component especially, maximally informative sequences of future observations. So in the special case where pragmatic value doesn't matter, like we have no preference over outcomes, We don't care if our bank account goes up or down. Then we implement a pure InfoMax novelty search. In a situation that's totally known, there's no epistemic value to be obtained, we have a special case of pure utility pragmatic value. However, in cases where both utility, pragmatic, and epistemic are on the table, G is proposed to resolve this dilemma by adjusting the action prior into an action posterior that respects the importance of both of those imperatives. That's the unified imperative of action and inference.
Yeah, so I'm not sure how I should understand this. So, for instance, I want to go to the baker and buy some bread, and then the most informative, I mean, the more unlikely thing is actually that I go to the barber and cut my hairs. So I would because that has more information than going to the baker and considering what kind of bread I'm going to buy. I go to the barber because that is more informative. I'm not sure I understand how I should understand this.
These values are calculated about generative models, not about territories. So it's natural and intuitive to want to be like directly mapping from an equation or calculation to a real world territory situation. But keep in mind, these are ultimately numerical values calculated for a generative model. It doesn't make sense to talk about free energy being minimized, like, for example, of a person doing translation simply, or of an ant simply foraging. It's of the generative model that these values are being calculated on. And so if one proposes a generative model of location behavior, so kind of in a previous discussion, we had like a higher order, like what location am I going to? Barber, home, baker, and then we have a lower level model with our footsteps. So that's kind of analogous to the livestream 42 SLAM robotics example. Then in that situation, one could ask how different policy selections were being influenced by their respective epistemic or pragmatic value. But it is not the case that we can directly draw from a variable to the territory. These are like summary variables or reweightings on our map. And it only makes sense to talk about these summaries on maps, not territories. Ali?
Actually, Michael Levin has an excellent paper from 2019, The Computational Boundary of a Self, in which he has an interesting diagram showing the cognitive sphere or cognitive light cones, if you will, of each cognitive or intelligent agent in which it can have an effect, and it's of more or less of its concern. So it also integrates that's it. So for example, for humans, because of or highly intelligent species or agent, because of the complexity of its goal-directed activity and agency, it results in a kind of larger cognitive boundaries, and for somewhat, let's say, quote-unquote, simpler agents, that would result in a much smaller light cone area of cognitive boundaries. Depending on the complexity of the tasks that the agent is capable of doing, that territory of its cognitive effectivity would vary according to the complexity of the tasks.
Yeah. So these are, G is a functional that is going to sharpen our action prior according to such and such. If we just wanted to pass through habit, we would just pass through habit. And in chapter 5, in the nervous system example, this is what's reflected in the bottom here with this dopaminergic circuitry, where on the left side of this basal ganglia or whatever mammalian tissue it happens to be, on the left side, there's kind of like a habit pass-through. Like E, the prior on affordance, is basically passed through. Whereas in G, on the right side, G is sharpening the policy distribution. So if we just want to pass through habit, we don't even need to apply G. However, if we want to sharpen our action selection in the moment to respect expected free energy in a prospective planning-like fashion, then we want to calculate G. So what is being calculated with G? Again, this is in equation 2.6, but also here we're taking another look at it. So there's two terms. Looking first at the pragmatic value. And the special cases were already mentioned and elsewhere about when one of these or the other is 0. Okay, so fancy E, it's an expectation regarding our Q variational distribution that we control of O tilde observation sequence conditioned upon policy. So we're going to see that both terms are conditioned upon policy. So if there's only 2 affordances, then we're only going to compute 2 different G's. So this is how we kind of prevent like spiraling and computing like all possible world futures. We're conditioning on action. And we're reducing our uncertainty about which actions to take. So that's what this first part is saying. It's expectation of the variational distribution of upcoming observation sequences conditioned upon actions, policies that we can take. And it is going to be a natural log to help facilitate just all kinds of things that logs facilitate, but it's a monotonic relationship with what is being described here. And this is about observations conditioned on preferences, C. So where observations are close to preferences, pragmatic value is high. Where our observations are different than our preferences, pragmatic value is low. Rather than associating pragmatic value with a reward function, we're associating it with bounding our surprise, natural log, self-information, surprisal, of our preference / expectation. The epistemic value component, which can be kind of seen as like a sub-function with like a negative I. But it's interesting that also this is kind of a surprisal, like even pragmatic value enters into an information theoretic surprise-like formulation. So even our pragmatic value is still informational. It's not, tokens. Here we see, again, an expectation over our variational distribution, but here, rather than on the sequence of observations through time, O tilde, it's the sequence of hidden states through time. So this is now looking at the underlying latent states conditioned upon policy. And there's a difference of 2 entropies. Then here's P, which is like the kind of actual distribution, and then Q, the distribution we control. Now within the parentheses, O tilde in both cases, O tilde conditioned upon states minus O tilde conditioned upon policies. So there's definitely a few ways to unpack it, and I think we've explored some, but broadly, if the policy is not further reducing your uncertainty about this relationship, the epistemic value is low. If the policy is reducing your uncertainty about S via O, then there's epistemic value. I think there's like a lot of open questions that are pretty contextual. Like, how do these implicit or tacit understandings, like, how does the rat know that going to that Q location is going to reduce its uncertainty? How does it know the semantics of the left versus the right Q? How does it know what, this is not the whole story. But within the context of doing variational inference on a structurally determined model, this is the basis of the separation between pragmatic value, defined as alignment between observations and preferences, and epistemic value, defined as reduction of uncertainty, which is to say entropy, of how policies sharpen our understanding of the relationship between hidden states and observations. Michael?
Yeah, so both of these are expectations, so that that is with respect to future things that might happen.
Both of these expectations are actually used in the sense of a mean. The time horizon is implicit within pi. Whether that is being calculated, whether G is being calculated over pi of length 1, 2, 3, etc. in the discrete time formalization. But these expectations are actually like center of gravity, Laplace approximation, central limit theorem, think expectation of a distribution. Even though it's like about the future, we're actually computing like the center of gravity for policies of different times. But we're not, funny enough, like we are, but we aren't talking about future time.
Okay, so what I maybe don't really understand here is the difference between P and Q. I was of the understanding that P is something that we that is present in the presence that we experience, and Q is something that happens in the future. Now I'm a little bit confused because P and Q both relate here in this equation to the future, right? So how can this be understood?
The difference between P and Q is not between the present and the future. P is like the underlying distribution, and Q is our variational approximation. So this is like the actual entropy of the relationship between observations and hidden states. Whereas this is the relationship of the entropy of the variational generative models relationship between those two. Ali?
Yeah, I think equation 2.3 might help to somehow clarify that ambiguity between P and Q, because in equation 2.3, yeah, that's it. The KL divergence between Q and P is defined as the expectation between the surprisal of Q and the surprisal of P. And one interesting thing about equation 7.4 is that the epistemic value is the expectation with respect to the hidden states, but the pragmatic value is the expectation with respect to the observations. So we need to keep both of them in mind, because here, as Daniel just mentioned, P is just the Q is the variational, free energy, but P is the standard the standard probability function we apply to a random variable. So that's why they have distinguished between those two functions, because Q has some a specific definition. So, for example, in equation 2.2, the probability of P without any, that's just the simple derivation of the probability of a random variable being of a specific value is calculated without taking into account Q's or other parameters.
Nice. Yes, the fact that pragmatic value is associated with outcomes is what ties closely to perceptual control theory. And the fact that epistemic value is associated with hidden states is related to the avoidal of overfitting. We're not reducing our epistemic value on observations. Observations are being evaluated for their pragmatic value. Hidden state inferences are being evaluated, and through them, policies are being evaluated for their epistemic value. Michael?
Yeah, so I'm a little bit confused about this. You said that Q relates to the variational free energy, but the variational free energy, I mean, we made this distinction between the G, which is the expected free energy, and the F, which is the variational free energy. And now inside that expected free energy is a variational free energy.
So, yeah, just to be clear,
confused.
Q is the variational distribution. This is the guy we control. Q is the guy we control. P, we don't. Mind your P's and Q's. Q is the one we control. Variational free energy is a real-time functional that's a function of our variational density Q and incoming data. It doesn't engage with planning. Expected free energy and a host of cousins like free energy of the expected future that Baron Millage and others have proposed. So this is not like the only way to even do this energy-based method in the future. This is, rather than a function of taking in only Q and Y as arguments, here the primary argument is the policy prior vector. And then the computation of this functional involves Q, the variational distribution. But like Q could be a Gaussian distribution. So we'd be looking to parameterize the variational parameters, the median and the variance, the two parameters of a Gaussian. And the true generative process may not be Gaussian. But we would be looking, just like in a linear regression, we'd be looking to minimize the sum of squares with the L2 norm. In this variational inference setting, we'd be looking to fit the best Gaussian, mean and variance, given the family of the variational distributions that we had chosen. Ali?
Yeah, so one other angle can be E is the actual posterior probability that is calculated according to the actual states we have at our disposal. But Q is the approximate posterior, so it's not the exact posterior that has been calculated in P. But yeah, Q is related to variational free energy in the sense that it's deployed in calculating the variational free energy, because for in order for the free energy to be a tractable parameter, to be, implementable in a computational task, we need to use this approximate variational free energy, because otherwise we don't have either all the information we need to calculate the exact posteriors, or it's too intractable to compute. So that's the reason behind using approximate variational free energy.
Great. And I think one kind of Leslie Valiant, this idea of like probably approximately correct, which is kind of like when they say almost surely in math, but more on the statistics side. If it's probably approximately correct, it's like actually within the context of approximate Bayes, that is what is going to be not just good enough, but like as good as you can kind of aim for. Okay. Matrices are defined. A has two slices, A1 and A2. We're going to give it as two modalities of A. And the dimensionality is clear in the MATLAB implementations. It's clear in the PyMDP. It's not exactly the same syntax, but like the structure of these matrices in principle are the same. A1 is describing the probabilistic mapping from location to exteroceptive cues. So it's not exactly an identity matrix, but basically this is the accurate GPS sensor. When it's at this location, start location, it knows exactly where it is. So again, you can be like, well, how does it get this implicit knowledge of where it is? Right. That's part of the complexity of cognitive modeling. But suffice to say that we're in a setting where the location is known without error. But one can imagine that there would be different outcomes and the need to do different parameterizations if like there were off diagonal elements. A2 is the probability, so they sum across to 1, they the columns sum to 1, about the food location, the between the spatial location and then the outcome of food. So semantically, this represents beliefs about food location in the A. Here, 7.5 is the same as 7.4. It's just that here it's like 2 in the upper left, 98 on the off. Here we see 98 on the upper left, 2 on the off. Here we have 1 in the third row, empty on the second. Here those two rows have been flipped to represent the black on the left side versus the black on the right side. So the food can be either on the left or the right side. The rat can either make the move to go to the left or the right side, or can go to the Q. If it decides to go for the Q, not the Q letter, but the CUE, if it decides to receive an informational cue, then it will find out where the food is. Again, check out Model Stream 7.2 with the epistemic foraging and all of that sort of stuff. Okay. These slices of B are describing movement affordances. Because again, with respect to the hidden state being location, B describes how different policy selection bears upon hidden states changing through time. C is describing the relative preference for different outcomes. So, the C1 vector is about the first modality. 5 of them. That's the locations, and there's a negative for the starting location. So that's like a little bit of like a kind of get going. Because if it preferred the start location, it might just stay there. Then in the second modality, that's referring to this shorter vector of these 1, 2, 3, and that's these 1, 2, 3. In various modeling settings, we've already started to see that like the C scaling matters a lot. And so that's one reason why I think it's tentative or hypothetical to say that simply like equation 7.4 resolves explore exploit, because it sets up the space for explore exploit to be framed. Absolutely, it does. However, depending on how the variables are parameterized, you can end up with an agent who still goes for the pragmatic value every time, or who still goes for the information value every time. So in terms of outcomes, it's not simply resolved by knowing what equation 2.5 is, but rather this opens up a space of modeling in which adaptive solutions can be reached. So if this was 6,000, then 0, 6,000, 0. It's like reward is so good, it's going to be pursued. If this was flat, 0, 0, 0, then it would be pure epistemic information. So that's why it's so important that we develop statistical power methods and parameter sweeps across simulations, because just making one T-maze and saying like, oh, look, the rat does this or that, it's kind of like, okay. D also is described for the two modalities, and it describes the priors on the two. There's a belief about the first location. I'm actually I'm a little bit curious why there's 5 elements here, but only 4 elements here. And then in the second modality, there, which again is referring, maybe this is like a minus, there's 1 fewer element here because there's only 2 here. Here's like reflecting an equal prior over where the food is. So a priori it's 50-50 left or right. So do you do a 50-50 bet left or right on the food, or do you go to get the epistemic cue, which of course reduces your uncertainty about where the food is? Now we're going to dive a little bit deeper into epistemic value itself. So in 7.4, they're saying we're going to go ahead and call just the epistemic value decomposition term I. Equation 7.8. So here is just a separation of as it was written in the prior equation. That is going to be rewritten in terms of a KL divergence. Q, S and pi, Q and S and pi. They're the same on both sides. Here's POS, here's QO pi. And it's definitely worthwhile, I think, for us to write out what these verbally mean, because they have very, I think, interesting implications for again, like what is the epistemic value? And then here is with this semicolon being noted, this is reflecting a pure information gain, salience, Bayesian surprise imperative. Here's some simulations showing at like time 2, it goes to the get the information, and then it proceeds to the left. Ali?
Yeah, just about your previous remark about why C has 5 elements and D has 4 elements, because C actually corresponds with the elements of A matrices. So because A matrices actually describe the hidden states that the environment is dealing with, but because D corresponds with B matrix, and because B matrix is a transition matrix, that's why we don't need to have a redundant additional element for that. So D being priors, it maps onto B matrix.
Thanks. And right now, like, you have to like specify the tensor dimensionality and add some labels, but they're developing a lot of functions in PyMDP, and people who work with it can definitely have a lot of feedback on slightly more intuitive and scalable ways to specify dimensionality, which is currently one of the rate limiting steps in PyMDP application. Okay. Just getting through 7, and then just so we can look ahead to 8, continuous time. So, precision, negative entropy, neg entropy. This is the high temperature and low temperature. High temperature, differences are erased. Low precision. Low temperature, absolute zero. High precision, differences are accentuated. That has technical usage, especially in certain statistical distributions. Isochade paradigm, Parr and Friston 2017. Isochading is, while our eyes may dwell on what we may associate with pragmatically valuable, broadly speaking, isochading is driven by information gain. So it's a great place to study how pragmatic semantics at a higher level are in a predictive processing type relationship with isochading at a lower mechanical level, with this level almost surely being driven by information gain. Learning and novelty here, one kind of question that was arising was like, why is there a dashed line between only here? But apart from that, priors are being provided on A and B. So that's sort of like the, again, and it's like a little bit like, why is B over here? So it's about the topology, not the geometry in this situation. What's happening is that a prior is being provided on A so that these A and B, in principle, can be learnable. How that plays out and how that influences the pseudocode of the action perception loop, PyMDP is very clear about that. Conjugate priors, this is facilitating, like, amongst other abilities, the Dirichlet conjugate prior for the categorical distribution. So if we have probability distribution over categorical outcomes, is it hot or cold? Then the Dirichlet can be used in an urn counting way. Like every time you observe a warm day or a cold day, you just put in a ball of that color into the urn. And then it could be 2 and 2. And then the next ball is very influential. It could be 1,000 and 1,000, and then the next ball is not so influential. And that turns out to be what's called a conjugate prior that enables the categorical distribution to stay as a classical probability distribution, Kolmogorov's axioms and all of that, while also allowing the conjugate prior to have this like counting or learning by counting strategy. Inferential approach to learning. This is a difference with many other areas. They're proposing learning schemes that may or may not be biologically relevant. Whereas a lot of work has gone into understanding how the perceptual or fast inference and learning or slower parameter learning processes are unified but of distinct timescales in active inference. Here in 7.11 equation, they are going to delve more into like learning as active. Yes. It's about policy. Everything's being conditioned upon policy. There's a lot that one can say about the integration of action. So this maze learning task is fundamentally intertwined with the action selection. The agent's updating of their likelihood is related to their action selection amidst uncertainty. They're not seen as like two separated phases. Here's where they just drop some kind of threads, and further literature, maybe further versions of the textbook are going to come into more detail. Hierarchical deep inference, nested modeling, something that people talk and think about a lot. But here we see the figure 4.3 or figure 7.3, the rake and the policy selection fractal. It's a rake of rakes. And structure learning and Bayesian model reduction. Just some model comparison and analysis techniques that support Bayesian statistics. Another example involving a hierarchical inference model is described, and that has been used in the context of reading and other visual inference tasks. That's chapter 7. Let's quickly look to chapter 8. Chapter 7 was discrete time generative models. Chapter 8 is going to be continuous time generative models. The main setting in which discrete time models have been studied is central or cognitive decision-making, categorical decision-making. In contrast, the major setting in which continuous time active inference models to this time have been used is in continuous movement or motor control tasks. So like in livestream 46, ActInf models do not contradict folk psychology with Alex Kiefer, Ryan Smith, and Maxwell Ramstead. They talk about like motor AI, MAI, and decision active inference, DAI. Here, there's going to be a proto-Bayesian physics-like representation that's going to enable us to do continuous things. Specifically, the separation of a data observation sequence in terms of an underlying function and a fluctuation stochastic term, and then a latent state derivative with a little dot. Change in latent states as a function of the current status of the hidden state and slowly varying causes, which are going to be playing the role of policies in continuous time formalization, and again, partitioning out of our stochastic fluctuations. So actually this part is guaranteed to have zero mean. And that's what facilitates like Bayesian mechanics, a lot of other statistics. Again, just like quickly looking through it, this Y, G, X, and F relationships continue to be built up to again talk, and this is very SPM-like. Here's our actual sensor readings from the EEG, fMRI, MEG. They're a function of neural activity. Neural activity is a hidden latent state. It is a function of current neural activity and attention, for example. That physics analogy in the continuous state space can be extended into Newtonian dynamics. And as Dalton and Bayesian mechanics have laid out in the last year or two, it goes way, way further than this. But this is a spring. So this is Hooke's law as a mere active inference entity. This is like a boring active entity that just dampens. But it's just to show that we can understand the generalized coordinates of motion, which is to say position, velocity, acceleration, snap, crackle, pop, etc., 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 generalized coordinates of motion within this continuous time framework. Dynamical systems, often which are conditioned to be smooth and differentiable, are amenable to continuous time formalizations. In the discrete time, we'd say, well, we have 1, 2, and 3, and then we're going to be moving to one of the locations in the grid world. And we have a transition matrix over grid world. In the continuous time setting, here, this is the spinal cord with the butterfly. Here's the sensory data coming in, Y, and then a descending hidden state inference and error deviation that's being resolved through policy selection in the continuous space. So this is hearkening back to chapter 5 and the spinal cord reflex, how continuous time generative models can be applied to continuous spinal motor reflexes as opposed to the usually more centrally associated discrete categorical decision-making DAI. There's a sidebar on precision attention and attenuation. There's the discussion of Lotka-Volterra, which is also called predator-prey or winnerless dynamics. Like, you can't win in this ecology. There are ecologies that collapse, of course, but activity dynamics amongst brain regions have been modeled for decades as these winnerless competitions, also called neural Darwinism, and that's relating to Friston's lineage with Edelman. More examples of how these kinds of winnerless competitions can be used in the context of continuous time generative models to generate smooth action sequences, like this sort of gibberish cursive writing. Learning is approached in a continuous model. Everything in chapter 8 is kind of being contrasted or juxtaposed with what we saw in chapter 7 in the discrete time. They introduced the Lorenz attractor, which is unpacked in significantly more detail in livestream 32 on Markov blankets and stochastic chaos. It is basically this example with the Lorenz attractor, which is showing that generalized synchrony, which isn't lockstep, but rather mutual information amongst coupled dynamical systems, can happen even when those coupled dynamical systems are Lorenz attractors. They don't have to be like both like simple linear systems. So that's like good to know. And they've used that to simulate bird song, where before learning, they're kind of like on and off a synchronization manifold, and then after learning, they've sharpened their joint distribution. Again, this begs further questions. How do they know the semantics of the song, and how do they learn the song? But this is just an example at this level of complexity. 8.5, hybrid models. Here we have the rake within a rake, but notice that the outer rake, there should be a line connecting this G to pi. The outer rake is DAI. Here we see hidden states through time, t minus 1, now, future, tale of two densities, observations through time, classic DAI, chapter 7 up top. But the nested model has the same structure, figure 4.3, but here we see the position, velocity, acceleration, generalized coordinates pattern occurring. So this is called a hybrid model because the discrete time model is nesting a continuous time model. So this has been used to model things like, where do I want to look from a categorical perspective? And then here's the oculomotor saccades at a continuous model that's nested within that. More equations, iSaccade model, more equations, summary, and key advances in continuous time models. End of the chapter. All right, thank you. We'll take a break and then begin with the next cohort in just 2 minutes.